Right now, as you read this, a galaxy is falling toward you. Not metaphorically, not eventually. Right now, at this exact moment, 2.5 million light-years away, the Andromeda Galaxy is moving in your direction at approximately 110 kilometers per second. That is 396,000 kilometers per hour. Fast enough to circle the Earth 9 times in 60 seconds. And it has been moving toward you, toward us, toward everything we call home, for longer than our species has existed. In 4 billion years, it will arrive. But here is the thing that should stop you cold. The number, 4 billion years, sounds safely remote, comfortably distant, a problem for beings so far in the future that they share nothing with us. And that feeling is exactly wrong, because the collision is not a future event that hasn't started yet. It started billions of years ago. The Milky Way and Andromeda have been gravitationally locked since before Earth existed. The approach has been underway for longer than complex animal life has been on this planet. We are already in it. The fall has already begun. We are passengers on a collision course that was set before the first fish developed legs. And Andromeda itself, the thing that is falling toward us, is something that most people have never genuinely confronted. Not its name, not the fact of its existence, not the pale smear it makes in the night sky above a dark field, but its actual nature, its actual scale, the reality of what it is. That reality will take you apart, not because the number is large, because the number is large in a way that changes how you see everything else. Let's start with what you can actually see. On a clear autumn night in the northern hemisphere, far from city lights, you can find Andromeda with your naked eye. It appears as a faint, elongated smudge in the constellation of Andromeda, not a point of light like a star, but a diffuse glow, slightly elongated, perhaps the apparent size of 6 full moons laid end to end. It is dim enough that people regularly mistake it for a cloud, or miss it entirely, or see it only in their peripheral vision, where the eye's light-sensitive rods are more concentrated than the cone cells in the center. That smudge, that faint pale streak, that thing you have to squint to see that disappears when you look directly at it, is a trillion stars. 1 trillion individual suns, each burning through its own nuclear fuel, orbited by their own planets, embedded in their own clouds of gas and dust, each one a story. The entire Milky Way, our galaxy, the galaxy that contains everything humans have ever touched or seen or thought about, holds somewhere between 200 and 400 billion stars. Andromeda holds 2.5 times as many. It is larger than us, more massive than us, more star-rich than us, and you can cover it with your thumb. Hold your thumb at arm's length against the night sky. The entire Andromeda Galaxy, 1 trillion stars, 140,000 light-years across, the largest structure in our local cosmic neighborhood, disappears behind your thumbnail. The thumbnail wins. This is not a failure of the universe, it is a statement about distance. 2.5 million light-years, that is how far away Andromeda is. To understand what this means in any genuine sense, not in the sense of being able to say the number, but in the sense of feeling the weight of it, requires some work. Let's do that work. A light year is the distance light travels in 1 year. Light moves at 299,792 kilometers per second. In 1 year, it covers about 9.5 trillion kilometers. In 2.5 million years, the distance to Andromeda, light covers approximately 23.5 quintillion kilometers. 23.5 quintillion. That is 23 and a half followed by 18 zeros. Numbers this large are not processed by the brain the way numbers in ordinary life are processed. When you hear that something costs $20, there is a felt sense, a calibrated intuition of what $20 is worth, what you could buy with it, whether it is cheap or expensive. This intuition is grounded in experience, in thousands of transactions and comparisons built up over a lifetime. There is no comparable intuition for quintillions. You have never held a quintillion of anything. Your ancestors never had to estimate quintillions of anything to survive. The neural machinery for processing quintillions simply does not exist in the human brain. When you hear the number, you process the word. You do not process the quantity. This is the honest starting point for any genuine confrontation with Andromeda's distance. We cannot feel it. We can only know it. And knowing it without feeling it is, in a specific way, enough. Let's try to build something close to intuition through comparison, knowing that every comparison will fail at the edges. Voyager 1, launched in 1977, now the most distant human-made object in existence, is currently about 24 billion kilometers from Earth. It has been traveling for 47 years, faster than any other spacecraft we have sent anywhere. At that speed, 17 kilometers per second, how long would it take to reach Andromeda? Approximately 45 billion years. The universe is 13.8 billion years old. It would take more than 3 times the current age of the universe for our fastest spacecraft to reach Andromeda. By the time Voyager 1 reached Andromeda at its current speed, the Sun would have long since died, the solar system would have dispersed, and the universe itself would have aged past the era of stars into the long twilight of stellar remnants. And here is the part that makes it stranger still. Andromeda is our closest large galactic neighbour. It is the nearest thing of comparable scale to the Milky Way in the known universe. In cosmic terms, it is next door. The distance to Andromeda, insurmountable, unreachable by any human technology in any time frame relevant to human planning, is local. It is the distance across the street, measured against the true scale of the observable universe. This is the first thing Andromeda teaches you. Not that the universe is large, that your intuition for large is wrong. Whatever you thought large meant, it was not large enough. Now let's talk about the moment when human beings first realized Andromeda was not what they thought it was. Because this is one of the most important moments in the history of science, and almost no one knows the name of the person who made it happen. For centuries, Andromeda appeared in astronomical catalogues as a nebula, a fuzzy patch of light among the stars, grouped with other fuzzy patches that were understood to be clouds of gas within the Milky Way. The Persian astronomer Abd al-Rahman al-Sufi recorded it in 964, describing it as a little cloud. He was the first person known to have written about it, though countless others had certainly noticed it. For nearly 1,000 years after al-Sufi, the nature of that little cloud was unclear. By the early 20th century, the debate had sharpened. Some astronomers, looking at the fuzzy patches called spiral nebulae, of which Andromeda was the most prominent, argued that they were distant island universes, separate galaxies far beyond the Milky Way. Others argued they were nearby gas clouds within our own galaxy. The disagreement was genuine, the evidence was ambiguous, and the stakes were enormous. The question was whether the Milky Way was essentially all there was, or whether it was one of many galaxies in a far larger cosmos. In 1920, This disagreement was formalized into what became known as the Great Debate, a public exchange between astronomers Harlow Shapley and Heber Curtis, held at the Smithsonian Museum of Natural History in Washington. Shapley argued that the Milky Way was enormous, much larger than previously thought, and that the spiral nebulae were nearby objects within it or just outside it. Curtis argued that the spiral nebulae were distant galaxies comparable to the Milky Way. They argued in front of a packed audience and resolved nothing. Both men made good points. Both made errors. The audience left without a winner. The resolution came 4 years later, not from either debater, but from a woman who had already done the foundational work that made the resolution possible, and who had largely been excluded from the argument itself. Henrietta Swan Leavitt was a computer at the Harvard Observatory. Computer in this context meant a person, almost always a woman, who performed the mathematical calculations that the male astronomers considered beneath them, or too time-consuming to do themselves. Leavitt's job was to study photographic plates, measure the brightness of stars, and record the numbers. She was paid 25 cents an hour. She was not expected to make discoveries. She discovered one of the most important relationships in all of astronomy. In the small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere, Leavitt identified a class of variable stars called Cepheids, which brighten and dim with a regular, repeating period. By studying hundreds of these stars, she noticed something extraordinary. The longer the period of the variation, the more intrinsically luminous the star. A Cepheid that brightens and dims over 30 days is genuinely brighter than one that cycles in 5 days, by a predictable amount. This is called the period-luminosity relationship. It means that if you can measure how fast a Cepheid is pulsing, you know how intrinsically bright it is. And if you know how intrinsically bright something is, and you measure how bright it appears from Earth, you can calculate its distance. The same way you can estimate how far away a street light is by how bright it looks if you know what wattage it is. Leavitt had given astronomers a cosmic ruler, a way to measure distances far beyond anything previously possible. She published her findings in 1912. She received minimal credit in her lifetime. She died of cancer in 1921, 3 years before the discovery she made possible was made. Edwin Hubble used Leavitt's period-luminosity relationship to find Cepheid variable stars in the Andromeda Nebula. By measuring their periods and apparent brightnesses, he calculated the distance. His result, published in 1924, was approximately 900,000 light-years, later revised upward to the current figure of 2.5 million light-years as calibrations improved. The Andromeda Nebula was not a cloud within the Milky Way. It was a separate galaxy, an island universe, incomprehensibly far away. The universe had just expanded in the space of a single paper from one galaxy to many. The Milky Way, previously assumed to be essentially all there was, had been revealed as one among an unknown number of similar structures spread across unimaginable distances. It was Leavitt's ruler. Hubble got the headlines. Now let's talk about what Andromeda actually is. Not its distance, but its nature, its structure, its contents. Because the scale of Andromeda is not only the scale of its distance, it is the scale of what is inside it. Andromeda is a spiral galaxy, like the Milky Way. Seen face-on, it would look something like a pinwheel, a bright central bulge surrounded by a flattened disk with spiral arms curling outward, traced by young hot stars and dark lanes of dust. But we do not see it face-on. From Earth's perspective, Andromeda is tilted at an angle of about 77 degrees to our line of sight, nearly edge-on, which is why it appears elongated rather than circular in the sky. Its diameter, approximately 220,000 light-years. That means if you stood on one side of Andromeda and shone a flashlight toward the other side, the light would take 220,000 years to cross it. 220,000 years ago, Neanderthals still walked the Earth. Its mass, approximately 1 trillion times the mass of the Sun, when you include all stars, gas, dust, and the dark matter halo that surrounds and permeates it. The dark matter halo, invisible, detectable only through its gravitational effects, extends far beyond the visible disk, perhaps to 1 million light-years or more. By mass, Andromeda and the Milky Way are roughly comparable, though estimates vary, and the comparison is complicated by how you define the boundary of each galaxy. Its stellar population, approximately 1 trillion stars. Imagine standing on a hill and being told to count the grains of sand on a beach. You can't. After an hour, you have counted perhaps a few thousand. You will not finish in your lifetime. You will not finish in 100 lifetimes. 1 trillion is 1,000 times a billion. If you counted one star per second, without sleeping, without stopping, it would take approximately 32,000 years to count Andromeda's stars. 32,000 years. Agriculture is 10,000 years old. All of human civilization in its entirety is not enough time to count the stars in one galaxy. And this is not the largest galaxy, not by a significant margin. The largest known galaxies contain tens of trillions of stars, dwarfing both the Milky Way and Andromeda. Andromeda is large by the standards of our neighborhood. It is not large by the standards of the universe. Let's give this a visual anchor, something to hold on to. The Sun is a dot, a yellow dot, roughly 1.5 million kilometers across, containing more than 99% of all the mass in the solar system. From Earth, it covers about half a degree of sky, the same apparent size as the full moon, which is why solar eclipses are possible at all. Now imagine shrinking the Sun down to the size of a grain of salt. A single grain of salt, barely visible on a tabletop. At that scale, the nearest star, Proxima Centauri, 4.2 light-years away, is about 11 kilometers from your grain of salt. Not 11 meters, 11 kilometers. You would need to drive for 15 minutes at highway speed to get from our Sun grain to the Proxima grain, and those would be two of the closest grains in the model. At that scale, 1 grain of salt per star, with stars 11 kilometers apart, the Milky Way galaxy is approximately 120,000 kilometers wide. That is nearly a third of the distance from Earth to the Moon. The galaxy at this scale is the size of the Moon's orbit. And Andromeda? At that scale, Andromeda is 2.5 million times 11 kilometers away. It is roughly 27 billion kilometers from your table. That is about the current distance to Voyager 1. To reach the nearest large galactic neighbor in our grain of salt model, you would need to travel the actual distance to Voyager 1. In the real universe, 2.5 million light-years, the same scale. The model breaks the mind in the right direction. Let's talk about what the collision will actually look like, because this is where the numbers become strange in a different way. In 4 billion years, Andromeda and the Milky Way will begin to merge. This sounds catastrophic. Two galaxies crashing into each other. The image that comes to mind involves destruction, collision, obliteration. It invokes the scale of impact and violence. The reality is more disorienting than the image. Stars are separated by enormous distances. The average distance between stars in the Milky Way's disk is several light-years. When Andromeda and the Milky Way begin to interact, The two galaxies will literally pass through each other, and the overwhelming majority of stars in each galaxy will never come close to any star in the other. The galaxies are mostly empty space. Two mostly empty spaces passing through each other produce mostly nothing. No star-on-star collisions, no explosions, no immediate destruction. What happens instead is gravitational choreography on a scale that defies visualization. As the galaxies pass through each other, the gravity of each galaxy distorts the other. Stars are flung into new orbits. The spiral arms are disrupted, pulled into long tidal tails that stretch hundreds of thousands of light years into space. The galaxies separate after the first pass, then gravity pulls them back together for a second interaction, then a third. Over the course of roughly 2 billion years, 2 billion years of repeated passes and interactions, the two galaxies gradually merge into a single, larger elliptical galaxy. Astronomers already know what this will look like. We have observed it happening to other pairs of galaxies throughout the universe. The Antennae galaxies, 62 million light-years away, are a pair of spiral galaxies currently in the process of merging, locked in exactly the kind of tidal interaction that the Milky Way and Andromeda will undergo. Their images show the long, curving tidal tails, the disrupted spiral structure, the burst of new star formation triggered by the collision of gas clouds. They are a preview. But here is the part that makes even astronomers pause. The Sun, our Sun, the star we orbit, the one that warms this planet, the one that makes life possible here, will almost certainly survive the merger. Not unaffected, but intact. It will be flung into a new orbit in the merged galaxy. It will be carried along with everything in the solar system. Earth, if it still exists, and it will have its own problems from the Sun's evolution by then, will be relocated to some position in the new elliptical galaxy, orbiting the same Sun, but in a galaxy that no longer looks anything like what we now call home. The night sky over Earth in 4 billion years will be spectacular in ways that beggar description. Andromeda, which now appears as a faint smear requiring dark skies and careful looking, will have grown to fill a significant portion of the sky. As the merger proceeds, over hundreds of millions of years, it will evolve. First, a vast complex structure spreading across the dome of the sky, then gradually settling into the diffuse glow of an elliptical galaxy surrounding the original Milky Way structure. No human will see it. No human descendant, by any reasonable projection, will see it. 4 billion years is long enough that the concept of descendant becomes meaningless. Anything alive to watch the merger will not be human in any sense that relates to us. But the merger will happen. The physics is settled, the trajectory is measured. The only question is which star the Sun will end up orbiting in the merged galaxy. And we cannot calculate that yet, because the chaos of the gravitational interactions makes precise predictions about individual stellar fates impossible over those timescales. What we can calculate is the overall outcome. 2 spiral galaxies, 2 trillion stars total, 1 merger, 1 new elliptical galaxy, provisionally nicknamed Milkomeda by astronomers, though it will need a real name when the time comes. Milkomeda, our grandchild galaxy, the structure that will inherit everything we think of as our cosmic home. We will never see it. It will be extraordinary. Now let's talk about something that is almost never discussed in accounts of Andromeda. The fact that the light we see from it is not the light that is there. When you look at Andromeda in the night sky, you are seeing it as it was 2.5 million years ago. The light entering your eyes left Andromeda before Homo sapiens existed, before Neanderthals existed, before Homo erectus had spread beyond Africa. The light you are seeing is older than our species. The Andromeda you see is not the Andromeda that is. It is the Andromeda that was, preserved in transit across 2.5 million light years, arriving at your retina after a journey that outlasted entire human lineages. What is Andromeda doing right now, at this actual moment? We do not know. We cannot know. The light showing us its current state will arrive in 2.5 million years. The Andromeda of now, whatever is happening in its spiral arms, whatever stars are being born or dying, whatever planets might exist around whatever stars, is invisible to us behind the veil of distance and the finite speed of light. This is true for every object beyond the Earth. The Sun, we see, is 8 minutes old. The nearest star is 4 years old. The centre of the Milky Way is 26,000 years old. Andromeda is 2.5 million years old. The most distant galaxies visible to the James Webb Space Telescope are more than 13 billion years old. Astronomy is archaeology. The sky is a record of the past at different depths. Every direction you look is a different moment in history. And here is the darkest edge of this truth, the part that tends to sit uncomfortably when you hold it properly. We do not know whether Andromeda still exists. Not in any practical sense. It almost certainly does. Galaxies do not typically disappear. But in the strict sense, we have no information about Andromeda's state in the past 2.5 million years. The light that would tell us is still en route. Anything that happened to Andromeda since before the first humans walked the savannah is unknown to us, and will remain unknown for millions of years. You are receiving information from a galaxy whose current state is inaccessible. You are looking at a message sent before your ancestors existed, from a sender whose current situation you cannot know. This is the real texture of cosmic distance. Not just the scale of the number, the epistemic isolation, the impossibility of contemporaneity. The way that the universe, at any meaningful distance, is always in the past, never in the present, never accessible now. Let's talk about the satellite galaxies of Andromeda, because Andromeda is not alone, and its companions add another layer of scale that almost no one considers. Andromeda has approximately 30 satellite galaxies orbiting it, caught by its gravity, circling it the way moons circle a planet. Some are small, irregular collections of millions of stars. Others are significant in their own right. M32 is one of Andromeda's most prominent satellites, a compact elliptical galaxy containing perhaps 3 billion stars, visible as a small patch of light near Andromeda's core. It was likely once a larger spiral galaxy that was stripped of its outer stars by Andromeda's gravity during repeated close passes, leaving only its dense central core. What we see as a small companion may have once been a galaxy comparable to the Large Magellanic Cloud. M110 is another satellite, a diffuse elliptical galaxy at the edge of Andromeda's disk, loosely structured, slowly being disrupted by the gravitational field of its host. The Triangulum galaxy, Messier 33, is sometimes considered a third member of the local group's dominant trio, though it is debated whether it is gravitationally bound to Andromeda or an independent member of the group. It is visible to the naked eye under extremely dark skies and contains roughly 40 billion stars. It is roughly 3 million light-years away. Together, the local group, Andromeda, the Milky Way, the Triangulum galaxy, and roughly 50 smaller companions, forms a gravitationally bound structure roughly 10 million light-years across. 10 million light-years. This is our cosmic neighborhood, our immediate environment. The collection of galaxies that gravity has bound together, that will eventually merge, that forms our home in the universe. And the local group, 10 million light-years of galaxies and gravity, is itself one small region of the Virgo cluster's outskirts. The Virgo cluster contains more than 1,000 galaxies and spans about 8 million light-years. The Laniakea supercluster, of which the local group is a tiny peripheral part, contains 100,000 galaxies and spans 500 million light-years. Andromeda is close. It is our nearest large neighbour, and from the perspective of the Laniakea supercluster, Andromeda and the Milky Way are essentially the same object. Two dots of light so close together that the distinction between them is invisible at supercluster scales. This is the nature of scale. Every zoom reveals more context. Every context makes the previous frame look intimate and small. Let's talk now about what Andromeda has already done to our understanding of the universe, not just through Hubble's discovery, but through what it has revealed about the nature of galaxies themselves. When astronomers in the 1970s began measuring the rotation curves of galaxies, how fast stars orbit at different distances from the galactic center, they expected to find a specific pattern. Near the center, where most of the visible mass is concentrated, stars should orbit fastest. At the edges of the visible disk, where mass is sparse, stars should orbit more slowly. The same way that outer planets in our solar system orbit more slowly than inner planets, in accordance with Kepler's laws and Newton's gravity. Vera Rubin and Kent Ford studied Andromeda. They measured the orbital speeds of stars across the full width of the galaxy, and they found something that should have been impossible. The stars at the outer edges of Andromeda orbited just as fast as stars near the center. The rotation curve was flat, not the declining curve that visible mass would predict. No matter how far you went from the center, the rotation speed stayed roughly constant. This violated every expectation. If the visible mass of Andromeda were all the mass in Andromeda, the outer stars would fly off into space. They were moving too fast to be held by the gravity of what could be seen. Something unseen was providing additional gravity, something massive, spread throughout the galaxy and beyond the visible disk, invisible to all telescopes, but inescapably real in its gravitational effects. Rubin and Ford had found the first convincing evidence for dark matter. Not theoretical, not inferred from cosmology, direct observational evidence from the orbital dynamics of a galaxy they could study up close, or as close as 2.5 million light-years allows. Dark matter, the invisible, unidentified substance that constitutes about 27% of the universe's total energy content, was revealed through Andromeda's rotation, through the motion of stars in the galaxy that falls toward us in the night sky. Rubin published this work through the 1970s. She was not awarded the Nobel Prize. She died in 2016. The Nobel for the confirmation of dark matter's existence has not been awarded, in part because no one has identified what dark matter actually is, despite decades of experiments designed to detect it. The rotation curve of Andromeda helped reveal that 95% of the universe is made of things we cannot see and do not understand. Dark matter, dark energy. The visible universe, every star, every planet, every galaxy, every atom, is 5% of what exists. Andromeda gave us the first clear look at the other 95. Let's talk about what the approaching collision actually means for the question of life in our galaxy, and why the answer is more complicated than it first appears. The standard framing is that the Milky Way-Andromeda merger is a catastrophic event for any life that might exist in either galaxy. Disrupted planetary systems, increased stellar density, burst of radiation from new star formation, and the reactivation of the supermassive black holes at the centers of both galaxies. The black hole story is worth pausing on. The Milky Way has a supermassive black hole at its center, Sagittarius A star, with a mass of approximately 4 million solar masses. Andromeda has one too, much larger, with a mass estimated between 100 million and several billion solar masses. When the galaxies merge, these two black holes will not immediately collide. They will spiral toward each other, losing energy through gravitational wave emission, potentially taking hundreds of millions to billions of years to finally merge. The merger of two supermassive black holes will produce the most energetic gravitational wave event in the observable universe's history, detectable potentially by any civilization with the right instruments at distances of millions of light years. But before they merge, as the galaxies interact and gas funnels toward the central regions, both black holes may light up as quasars, active galactic nuclei, blazing with energy from accreting material, outshining entire galaxies. Two quasars in the same merged galaxy, potentially flooding the surrounding regions with radiation. This is not good for life anywhere near the galactic centers. But most stars are not near the galactic centers. The Sun is 26,000 light years from the Milky Way's center. In the merged galaxy, the Sun, or its remnant, will be flung to some distance from the new central region, in an orbit shaped by the chaotic dynamics of the merger. Probably far enough that the quasar phase, if it occurs, is not immediately sterilizing. Probably. The honest answer is we do not know what the Sun's specific orbit will look like in 4 billion years. The orbital mechanics of individual stars through a galaxy merger are chaotic in the mathematical sense. Small uncertainties in initial conditions compound over billions of years into large uncertainties in final states. We can calculate the overall shape of the merger. We cannot calculate where any particular star ends up. What we can say is this: galaxy mergers happen constantly throughout the universe. We observe them at every stage, in hundreds of systems. Life, if it exists in merged galaxies, if it existed before the merger and survived, has presumably navigated this process in many other locations. The merger is not necessarily terminal. It is disruptive. It is long. It is transformative. It is coming regardless. Let's talk about the Andromeda Galaxy's satellites in a different way, as a demonstration of the hierarchical structure of the universe and what that hierarchy tells you about scale. The Moon orbits Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way is gravitationally bound to Andromeda and the other galaxies of the local group. The local group is part of the Virgo supercluster. The Virgo supercluster is part of the Laniakea supercluster. Laniakea is a region of the larger cosmic web. Each level of this hierarchy operates on a scale that dwarfs the previous one. The Moon is about 380,000 kilometers away. The Sun is 150 million kilometers away. The galactic center is 26,000 light years away. Andromeda is 2.5 million light years away. The Virgo cluster is 53 million light years away. Laniakea spans 500 million light years. At each step, the scale increases by a factor of roughly 100 to 1,000. The jump from Moon to Sun is about 400 times. The jump from Sun to galactic center is about 160 million times. The jump from galactic center to Andromeda is about 100 times. The jump from Andromeda to the Virgo cluster is about 20 times. The jump from Virgo cluster to Laniakea is about 10 times. We are embedded in structures within structures at every scale. And at every scale, our position looks smaller against the next level up. From the surface of the Earth, the solar system seems vast. From the scale of the solar system, the Milky Way seems vast. From the scale of the Milky Way, the local group seems vast. From the scale of the local group, Laniakea seems vast. From the scale of Laniakea, the universe continues for billions of light years more, with structures at every scale. The cosmic web, the large-scale structure of the universe, is itself organized into filaments and walls and voids that span hundreds of millions of light years. The largest structures known extend to billions of light years. The Hercules Corona Borealis Great Wall may span 10 billion light years. A single coherent structure 10 billion light years across in a universe 13.8 billion years old. Andromeda, the scale of which has occupied us throughout this exploration, is a point on the map of that great wall. Less than a point, an infinitesimal location within one filament of the cosmic web. This is not the end of the scale story, it is the middle. Let's talk about what happens to Andromeda in the very long term. Not the merger with the Milky Way, which happens in 4 billion years, but what happens to the resulting merged galaxy over timescales that make 4 billion years look like an afternoon. After the merger, Milkomeda, or whatever it is called, settles into an elliptical galaxy. No more spiral arms, no more lanes of cold gas generating new stars. A more uniform, diffuse structure of older, redder stars, still containing the remnants of everything that was once the Milky Way and Andromeda. Star formation will slow dramatically. Elliptical galaxies, lacking the cold gas reservoirs of spiral galaxies, form few new stars. The existing stars will age. The most massive will already have died in supernovae during the merger itself. The Sun will have exhausted its fuel and become a white dwarf by the time the merger completes. The remaining stars in Milkomeda will, over tens of billions of years, slowly use up their fuel and die, becoming white dwarfs, neutron stars, black holes. In roughly 100 trillion years, the end of the stellar era, the last red dwarfs in Milkomeda will exhaust their fuel and fade. The galaxy will go dark, not empty, still full of stellar remnants, dark matter, black holes, but dark. No more starlight. The galaxy that was once 2 trillion blazing suns that lit the local universe for billions of years will be a cold, dark cloud of remnants falling through the cosmic void. And the void, by then, will be much larger. The expansion of the universe, driven by dark energy, will have carried all other galaxy groups beyond the cosmological horizon. Milkomeda, in 100 trillion years, will be, essentially, alone. The local group will have merged into a single structure, and every other galaxy cluster will have receded beyond the point where its light can reach us. The universe will appear, to any observer in Milkomeda, to consist of one island of matter surrounded by emptiness. The isolation that now requires telescopes to appreciate will have become absolute. Andromeda, which appears as a smear of light in our sky, evidence that we are not alone, that our galaxy is one of many, that the universe extends beyond us in every direction, will have merged into our own structure. And then, eventually, there will be no sky to look at, no light to carry information about the universe, no evidence remaining from within Milkomeda that anything else ever existed. The universe erases its own history. The merger of Andromeda and the Milky Way is not only a physical event, it is the closing of an epistemic window. The evidence of cosmic companionship, the evidence that we are not alone, will eventually be swallowed by the very process of that companionship. This is the dark angle that the scale of Andromeda contains. Not just that it is large, not just that it is falling toward us, but that its approach is the approach of the last neighbour we will ever have, and that after the merger, after the long settling into Milkomeda, after the stars burn out, the record of everything beyond will be gone. The smear of light in the autumn sky is not just a galaxy. It is the universe's evidence of itself. And it is, slowly, falling home. Let's talk about something that almost no one considers when they think about Andromeda. The fact that the stars inside it are not evenly distributed, and what that uneven distribution reveals about the galaxy's violent history. Andromeda is not a clean, pristine spiral. Look at it through a large enough telescope and you begin to see the scars. Shells of stars, concentric rings of stellar material spreading outward from the core. Streams of stars, long thin arcs trailing through the galaxy's outer regions like brushstrokes on a dark canvas. Tidal debris spread across hundreds of thousands of light years, the remnants of smaller galaxies that Andromeda has consumed over billions of years. The giant stellar stream is the most prominent. It is an arc of stars wrapping around Andromeda's outer regions, roughly 20,000 light-years long, containing hundreds of millions of stars. It is the remains of a smaller galaxy, tentatively identified as a former satellite called M32P, that passed too close to Andromeda and was torn apart by tidal forces. What was once a complete galaxy, with its own structure and its own history, is now a river of stars curving through Andromeda's halo, still moving in the orbit it traced when it was whole, gradually dispersing into the larger galaxy. The encounter that produced the giant stellar stream happened roughly 1 to 3 billion years ago. Andromeda consumed a galaxy, and the meal left marks that persist to this day. The stars of that consumed galaxy are still there, still identifiable by their chemical composition and their motion, still tracing the ghost of a structure that no longer exists. Andromeda is an archive of everything it has eaten, and it has eaten a great deal. Astronomers can read this archive by measuring the metallicity of stars, the abundance of elements heavier than hydrogen and helium. Stars formed from enriched gas, recycled through multiple generations of stellar evolution, contain more heavy elements than stars formed from pristine early universe gas. Stars from cannibalized satellites tend to have characteristic compositions that differ from Andromeda's native population. By mapping these compositions across the galaxy, astronomers reconstruct the merger history, a genealogy written in stellar chemistry. What emerges is a picture of Andromeda as a serial consumer. Over its lifetime, it has absorbed dozens of smaller galaxies, each one adding its stars to the growing mass, each one leaving faint structural echoes in the halo. The smooth outer disk we see in photographs is not smooth, it is layered, it is stratified, it is built from the remains of things that no longer exist as independent structures. This is how large galaxies grow, not primarily through the gradual condensation of gas, but through the consumption of smaller neighbors. Andromeda has been building itself by eating the universe around it, one small galaxy at a time. And in 4 billion years, we are next. The Milky Way is not a small galaxy. It is Andromeda's match in size. The merger will be symmetric in a way that Andromeda's previous meals were not. But the dynamic is the same. Two structures, bound by gravity, approaching a point of no return, destined to become one. The stars of the Milky Way will join the chemical archive of Andromeda. Future astronomers in Milkomeda, if any exist, will be able to trace from the metallicity and orbital characteristics of stars the contributions of both progenitor galaxies. They will see in the chemistry of the stars around them the history of the merger. They will know they live in a composite, a galaxy built from two. They will not know which stars came from which progenitor, not precisely. The mixing will be thorough enough over billions of years of orbital evolution that the distinction will blur. The Sun, or rather whatever stellar remnant the Sun has become by then, will be indistinguishable from the rest. The Milky Way, which we think of as home, will become an archaeological layer in someone else's history. Let's talk about the supermassive black hole at Andromeda's centre, and why it is one of the most extraordinary objects in our cosmic neighbourhood. Every large galaxy appears to have a supermassive black hole at its centre. The Milky Way's Sagittarius A star has a mass of about 4 million solar masses. It was directly imaged for the first time in 2022 by the Event Horizon Telescope collaboration, a network of radio telescopes spanning the globe, combining their signals to achieve an effective aperture the size of Earth. The image that emerged, a glowing ring of superheated gas surrounding a dark central region, is the shadow of the black hole's event horizon. The dark centre is not the black hole itself, which has no surface. It is the region from which no light can escape, defined by the boundary beyond which gravity is too strong for even photons to break free. The ring is the light of gas being heated to millions of degrees as it spirals inward. 4 million solar masses. Sagittarius A star is a relatively modest supermassive black hole by galactic standards. Andromeda's central black hole is different. Estimates of its mass range from 100 million to several billion solar masses. The uncertainty is large because the measurement is technically challenging. The galaxy's centre is complex, partially obscured by dust, and the orbital dynamics of stars near the centre that would constrain the mass measurement are difficult to measure from 2.5 million light-years. But the lower bound, 100 million solar masses, is already 25 times larger than Sagittarius A star. The upper bounds suggest it may be hundreds of times larger. A black hole of 100 million solar masses has a Schwarzschild radius, the radius of its event horizon, of roughly 300 million kilometers. That is approximately 2 astronomical units, 2 times the Earth-Sun distance. An object 2 astronomical units across, a region of space-time from which light cannot escape, at the center of the galaxy falling toward us. In the current epoch, Andromeda's central black hole is quiet. It is not actively accreting large amounts of material. It is not producing a quasar. It sits at the center of the galaxy, surrounded by old stars, its presence betrayed only by the orbital dynamics of things near enough to feel its gravity. When the merger begins, when Andromeda and the Milky Way begin to interact and tidal forces drive gas toward the central regions of both galaxies, one or both black holes may activate. Gas funneling toward a supermassive black hole forms an accretion disk, a swirling structure of superheated material that radiates more energy per unit mass than any other process in the universe. An active supermassive black hole accreting at high rates can outshine its entire host galaxy by a factor of hundreds. Andromeda's black hole, activated by the merger, could briefly become one of the most luminous objects in the local universe. From our perspective, if anything exists to observe it, the center of the merging galaxy could be brighter than the full moon. This is not certain. Some mergers activate both central black holes. Some activate one, some activate neither. The gas dynamics are complex, but the potential is there, locked inside the quiet center of the galaxy, currently visible as a smear in our autumn sky. Let's talk about distance in a different way, through the story of how we measure it and why the measurement itself is one of humanity's most profound achievements. The distance to Andromeda is known, not guessed, not estimated from vague principles, known, through a chain of measurements that begins with parallax, the shift in apparent position of nearby stars as Earth moves around the Sun, and extends outward through multiple calibrated steps, each depending on the previous, each extending the reach of measurement further into the universe. The parallax step was already extraordinary. Measuring the tiny angle, less than 1 arcsecond, 1/3600th of a degree, by which nearby stars appear to shift as Earth moves from one side of its orbit to the other, required patience and precision that bordered on obsession. Friedrich Bessel measured the first stellar parallax in 1838, using the star 61 Cygni, and found a distance of about 10 light-years. He had used the diameter of Earth's orbit, 300 million kilometers, as his baseline, and from the tiny shift in a star's apparent position, calculated a distance that no human had previously measured or conceived of in physical terms. The Cepheid step, Leavitt's contribution, extended the reach to other galaxies. The Type 1a supernova step, standardizable explosions of known intrinsic brightness, extended it to billions of light-years. The Hubble flow, the relationship between a galaxy's distance and its recession speed, extends it to the edge of the observable universe. The chain is calibrated at each step. Errors propagate. Current estimates of the distance to Andromeda are 2.5 million light-years, with an uncertainty of a few percent. The measurement is constrained by multiple independent methods: Cepheid variables, red giant stars used as standard candles through the tip of the red giant branch method, and the comparison of these with other distance indicators. 2.5 million light-years, known, measured, certain within a few percent. This precision is remarkable for something so remote. The distance to Andromeda was not obvious. It was not easy. It required more than a century of increasingly precise observations built on the work of dozens of astronomers, many of them uncelebrated, using instruments that improved in sensitivity with each generation. The number we state so casually, 2.5 million light-years, is the product of extraordinary human effort, accumulated over generations, refined by argument and observation and the slow, grinding progress of science. It is a measurement, not a guess. A measurement of the distance to another galaxy by creatures on a rock orbiting a minor star in the outer disk of a spiral galaxy in one small corner of the observable universe. This is worth pausing on, because it is easy to hear numbers about cosmic scales and feel diminished by them, to feel that the scale of the universe makes us small and irrelevant. But the measurement of that scale is itself an act of extraordinary ambition and extraordinary success. We reached out with instruments made of metal and glass, and we touched something 2.5 million light-years away. We measured it. We know it. The universe is larger than us. We are the part of the universe that measured it. Let's talk about light pollution, because the fate of our ability to see Andromeda at all is itself a statement about where we are. In 1965, before the widespread adoption of artificial lighting at modern intensities, the Andromeda Galaxy was visible to anyone on Earth with dark-adapted eyes and a reasonably clear sky. It was one of the most accessible naked-eye objects, a reliable companion to winter stargazing, prominent enough to be used as a navigation aid by ancient Persian astronomers, recorded by Al-Sufi more than 1,000 years ago. Today, the majority of people on Earth live under skies too bright with artificial light to see Andromeda. The Milky Way itself, the structure we live inside, the galaxy that contains our Sun, is invisible to more than 80% of the population of the United States and 60% of the world's population. The objects that humans have observed and documented for millennia have been hidden, within the span of a few decades, by the light of our own civilization. The nearest galaxy, the structure that is falling toward us at 110 kilometers per second, that contains 1 trillion stars, that has been visible to human eyes since before recorded history, is now invisible to most of the people alive on the planet from which it has always been observed. This is a loss of a specific kind, not the loss of something that can be recovered by reading about it or looking at photographs. The experience of looking up on a clear, dark night and finding Andromeda with your own eyes, following the chain of stars to the smear of ancient light, knowing what you are seeing, knowing the light arriving at your retina left that galaxy before your species existed. This is an experience that rewires something in how you understand your place in the universe. It is becoming unavailable to most humans. The loss of the dark sky is a loss of context, of scale, of the direct, unmediated encounter with the universe's actual dimensions that has been available to every human generation before ours and is being foreclosed by the brightness of our own civilization's infrastructure. And there is a specific irony in this that deserves to be named. The same industrial civilization whose growth has dimmed the sky is the civilization that built the telescopes, developed the mathematics, and generated the knowledge that allows us to understand what the sky contains. We know more about Andromeda than any previous generation, and more people in our generation cannot see Andromeda than in any previous one. We have the map, we have lost the territory. Let's talk about what Andromeda's structure tells us about our own galaxy, because one of the most productive uses of our nearest large neighbour is as a mirror in which we see the Milky Way from the outside. We live inside the Milky Way. We cannot see it whole. We see it as a band of light crossing the sky, a cross-section of the disk observed from an embedded point. We cannot step outside it, cannot photograph it from above, cannot easily determine its overall shape, its spiral arm structure, or its true dimensions from our position inside it. Andromeda is a spiral galaxy seen almost edge-on from our perspective. But other galaxies, seen from above at various distances and orientations, show us what spiral galaxies look like from outside. And by comparing the properties of the Milky Way, its mass, its stellar content, its rotation curve, its star formation rate, with those of comparable galaxies observed from outside, we can construct a picture of what our own galaxy looks like. The picture that emerges is of a barred spiral galaxy, one with a bar-like structure of stars running through its center, with spiral arms extending from the ends of the bar rather than from the core itself. This makes the Milky Way most similar not to Andromeda, which appears to be a more standard spiral without a prominent bar, but to galaxies like NGC 649 or the well-studied NGC 1365, galaxies whose bar spiral structure has been mapped in detail from outside. If you could photograph the Milky Way from above, it would look something like these galaxies: a bar of stars crossing the center, spiral arms wrapping outward, the Sun approximately halfway out on one of those arms, in a relatively quiet inter-arm region, the bright core visible from tens of thousands of light-years away, the dark lanes of dust tracing the regions of active star formation. This is our home, seen from outside, a structure no human eye will ever directly observe, reconstructed from observations of analogous structures seen from distances that make them small enough to photograph whole. We know what the Milky Way looks like. We have never seen it. We know it through the mirrors of 1 million other galaxies. Andromeda is the most important of those mirrors, the one close enough to show us detail, large enough to be studied in depth, similar enough to serve as a direct comparison. Everything we know about the large-scale structure of the Milky Way has been refined by comparison with Andromeda. The two galaxies have been studied together for decades, their similarities and differences used to constrain models of how galaxies form and evolve. When Andromeda merges with the Milky Way, we lose that mirror. We lose the nearest comparable galaxy. We lose the benchmark against which our own galaxy has been measured. This is another kind of loss, smaller than the others, but real. The merged galaxy will not have a nearby twin for reference. Milkomeda will be a larger, more isolated structure, the dominant galaxy in the local group, orbited by dwarf satellites without a peer. The loss of the mirror is, in the scales of cosmic time, trivial. But in the scales of scientific value, it matters. Andromeda has been telling us about ourselves for a century. When it merges with us, it will stop. Let's talk about the velocities involved in the collision, because the numbers tell a story that is both impressive and, at the larger scale of the universe, humbling. Andromeda is approaching the Milky Way at approximately 110 kilometers per second. This is the radial velocity, the component of its motion directly toward us, measured through the Doppler shift of its spectral lines. The transverse velocity, the component of its motion perpendicular to our line of sight, is smaller, about 20 kilometers per second, based on measurements from the Hubble Space Telescope tracking the proper motion of stars in Andromeda. 110 kilometers per second. This is fast by the standards of everyday experience. A commercial aircraft travels at roughly 0.3 kilometers per second. A rifle bullet travels at roughly 1 kilometer per second. A spacecraft at orbital velocity travels at about 8 kilometers per second. The Andromeda Galaxy is approaching us at roughly 14 times orbital velocity. And yet, at the scale of galactic distances, 110 kilometers per second is slow. At this speed, crossing 1 light year, about 9.5 trillion kilometers, takes approximately 87,000 years. Crossing the distance that currently separates Andromeda from the Milky Way, 2.5 million light years, takes roughly 22 billion years. The universe is not old enough for Andromeda to have come from arbitrarily far away at this speed. Andromeda and the Milky Way have always been close, cosmically speaking. They formed in proximity. They have been gravitationally bound since before either had reached its current size. What we are watching, the approach, is not a long journey from far away. It is the final phase of a dance that has been ongoing since the universe was young. The speed of approach is increasing. As the galaxies draw closer, gravity accelerates the fall. By the time of first contact, first significant interaction of the outer regions of each galaxy, the speed of approach will be several hundred kilometers per second. At the moment of closest passage, when the cores of the two galaxies come to their nearest point, the relative speed may be over 1,000 kilometers per second. 1,000 kilometers per second is approximately 1/300th of the speed of light, still well within the non-relativistic regime, still governed by ordinary Newtonian and Einsteinian gravity, not by the exotic physics of near light speed motion. The collision happens in slow motion by the standards of particle physics, and it is over. The two galaxies pass through each other in a period of hundreds of millions of years. Then they separate. Then gravity pulls them back. Then they pass through each other again, more slowly this time. Then again. Each pass dissipates energy and brings them closer to a merged configuration. The full merger takes approximately 2 billion years from first contact to final coalescence. 2 billion years of repeated interactions, of tidal disruption and gravitational chaos, of new star formation triggered by colliding gas clouds, of two supermassive black holes spiraling toward each other through the newly merged structure. 2 billion years. The time from the first complex animals to the present. The time from the first fish to us. And then as long again. The merger of Andromeda and the Milky Way is not an event, it is an era. Let's talk about what we know about the fate of the Sun specifically during this process, because the personal scale matters, and the personal scale here is genuinely strange. The Sun will be, by the time of first interaction with Andromeda, approximately 4 billion years older than it is now. It will have exhausted its core hydrogen and begun to expand into a red giant, a swollen, cooler star that will have engulfed Mercury and Venus, and possibly Earth. If Earth survives as a physical object, and it may, as the Sun's outer envelope is less dense than it sounds, it will be a scorched, airless rock, its oceans long since boiled away. The Sun, in this state, will survive the merger. A red giant, or later a white dwarf, the dense, cooling remnant that the Sun will leave behind, is a physically small, gravitationally bound object. The merger affects the orbit of this remnant, but not its existence. The Sun's remnant will be flung into some new trajectory in the forming Milkomeda, carrying with it the remnants of its planetary system. Where does it end up? Simulations of the merger show a range of possible outcomes for individual stars. Most stars from both galaxies end up somewhere in the merged elliptical structure. A small fraction are ejected entirely, flung out of the merged galaxy by the gravitational chaos, sent into intergalactic space as hypervelocity stars, to drift forever in the void between galaxy clusters. The probability that the Sun specifically ends up ejected is small, roughly 3% based on current simulation estimates, but it is not zero. 3%. The chance that our solar system's remnant, the dead Sun and its cold planets and moons, ends up as an intergalactic refugee, expelled from the galaxy that is being built from the merger of our home with Andromeda, drifting alone in the vast emptiness between Milkomeda and whatever else remains in the local group, is 3%. 3% is not alarming. 97% of the time we stay. We are incorporated into the new structure, new orbit, still inside the gravitational family. But the 3% is real, and it is a reminder that the merger, for all its grandeur, is also a process of randomness and chance at the level of individual stellar fates. The future location of the Sun's remnant is not determined by any large-scale structure. It is determined by the specific sequence of gravitational interactions, each one amplifying tiny uncertainties across 2 billion years of dynamical chaos. Chaos in the technical sense, sensitive dependence on initial conditions. The future cannot be calculated from the present, even in principle, because the precision required exceeds any physical bound. The solar system's fate in the merger is genuinely unknown. Not unknown because we haven't looked, unknown because the universe doesn't know yet. Let's talk about something that is rarely discussed when people talk about Andromeda. The fact that our collision with it is not unique, and that the universe is full of mergers in progress, at every scale, at every stage. The universe is not a static collection of isolated galaxies, each in its own private corner of space. It is a dynamic, continuously evolving network of gravitational interactions. Galaxies merge, groups of galaxies merge, clusters of galaxies merge. The large-scale structure of the universe, the cosmic web of filaments and voids, is the product of billions of years of matter falling together under gravity, hierarchically, from small scales to large. The antennae galaxies, 62 million light-years away, are two spirals in the early stages of their merger. The long tidal tails extending from each galaxy, the antennae that give the system its name, are streams of stars flung outward by the gravitational interaction. The system is producing new stars at a furious rate as gas clouds collide. It is what the Milky Way and Andromeda will look like in a few 100 million years. The mice galaxies, 290 million light-years away, are two spirals in a more advanced merger. Their tidal tails are longer. Their structure is more disrupted. They have already passed through each other and are beginning the second approach. NGC 4038. The Cartwheel Galaxy, 490 million light-years away, is the aftermath of a smaller galaxy passing directly through the center of a larger one, producing the distinctive ring structure from the expanding wave of star formation triggered by the impact. These are not rare or exceptional systems. They are samples from a population of merging galaxies distributed throughout the universe. At any given time, a significant fraction of large galaxies in the universe are involved in mergers or have recently completed them. Andromeda and the Milky Way are unremarkable in their mutual approach. The approach is not a special event. It is a normal component of how the universe evolves on galactic scales. This is the context for what we call our cosmic home. Not a stable, permanent structure, but a temporary configuration, a spiral galaxy that formed in the early universe, that has grown by accretion and merger, and that is currently in the approach phase of its next and largest merger. The Milky Way is not a permanent feature of the universe. It is a stage in a larger process. All of this, the local group, the merger, the eventual Milkomeda, is itself temporary. The merged galaxy will age, its stars will die, and it will eventually join the dark, cold universe of stellar remnants that fills the far future. Nothing is permanent at these scales. Everything is in motion. Everything is becoming something else. Andromeda, falling toward us in the night sky, is a reminder of this. It is not background, it is process. It is the universe in motion, doing what the universe does, assembling larger structures from smaller ones over timescales that dwarf everything we think of as long. Let's talk now about what Andromeda's future looks like after the merger. Specifically, what kind of object Milkomeda will be, and why it matters for the question of what the universe becomes. Elliptical galaxies, the type that galaxy mergers tend to produce, are qualitatively different from spirals. They are not simply larger spirals, they are a different phase of galactic evolution. The merger disrupts the ordered rotation that defines a spiral's disk structure. Stars that were following circular orbits in a flat plane are flung into random, elongated orbits inclined at all angles. The result is a diffuse, roughly spherical distribution of stars on random orbital paths, the defining characteristic of an elliptical. The gas that fed star formation in both spirals is used up during the merger, partly converted into stars in the burst of star formation triggered by colliding gas clouds, partly expelled in galactic winds driven by the radiation and supernovae from massive stars forming in that burst. The elliptical that results has little cold gas left. It makes few new stars. It ages. The stars in Milkomeda after the merger will be on average older and redder than the stars in either parent galaxy today. The blue light of hot young stars, which gives the Milky Way's star-forming regions their vivid colour in photographs, will fade as the last young stars age and die and are not replaced. Milkomeda, in maturity, will glow with the warm yellow and red light of aging stars. It will be beautiful, in the way that something very large and very old is beautiful. But it will be quieter than either progenitor, less active, further from the vigorous, messy star-forming processes that characterize young spiral galaxies. In this sense, the merger is a kind of aging. The universe's galaxies are, in aggregate, gradually becoming older and redder. transitioning from the star-forming spirals of the universe's youth to the quieter ellipticals of its maturity. Milkomeda, produced by the merger of two of the largest spirals in the local group, will be one of the universe's mature ellipticals, large, old, star-poor, dark matter-rich, slowly cooling toward the long future that awaits all galaxies. And it will be alone. The cosmic expansion will have carried all other galaxy groups beyond the horizon. Milkomeda, aging in isolation, surrounded by its dwarf satellites, will look out into empty space. No other galaxies visible. No evidence from any observation possible within its confines that other galaxies ever existed. The merger of Andromeda and the Milky Way is the last coalescence of our cosmic family. After it completes, the family is gone, merged into one structure, surrounded by nothing, aging together in a universe that will take trillions of years to finish what it has started. This is where the smear of light in the autumn sky leads. This is what Andromeda means, held to its logical end: a collision, a merger, an isolation, an aging, and a long, long darkness after the last star goes out. Let's talk about something that should unsettle you more than the collision itself: the fact that we are already inside Andromeda. Not metaphorically, literally, right now. Andromeda's dark matter halo, the invisible extended cloud of dark matter that surrounds and permeates the galaxy, reaches far beyond its visible disk. Estimates based on gravitational modeling suggest the halo extends to roughly 1 million light-years from Andromeda's center, possibly further. The Milky Way's own dark matter halo has comparable dimensions, and the distance between the two galaxies, 2.5 million light-years, means the outer fringes of each halo are already overlapping. The boundary between our galaxy and Andromeda, in terms of the dark matter that defines where one gravitational influence ends and another begins, is already blurred. We are already within the outer reaches of each other's gravitational domains. The separation of 2.5 million light-years describes the distance between the luminous, visible cores. The gravitational reality is already shared. Picture two soap bubbles floating toward each other. From a distance, they look separate, but as they approach, before they visibly touch, their surfaces are already interacting. The air pressure changes, the geometry shifts. The interaction has begun before the contact is obvious. The Milky Way and Andromeda are past the soap bubble stage. Their gravitational bubbles are already merging. We have been falling toward each other since before the universe was half its current age. The approach is not beginning, it is almost done. This reframe matters because it changes the way the collision feels. It is not a future event, it is the final visible phase of an ancient process. The crash that seems billions of years away is, in gravitational terms, already happening. The two galaxies are already entangled. The outcome is already determined. What's left is just the physics playing out. Let's talk about Vera Rubin more carefully, because the story of how Andromeda revealed dark matter is also the story of how science treats the people who make its most important discoveries. Vera Rubin was born in 1928 in Philadelphia. By the time she was 10, she was dragging her cot to her bedroom window to watch the stars through the night. By the time she was 17, she had decided to study astronomy. By the time she applied to the California Institute of Technology for graduate school, she received a letter informing her that Caltech did not accept women. She went to Cornell instead, then Georgetown, eventually joining the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. She was one of very few women in professional astronomy, at a time when the field treated female scientists as anomalies to be managed, rather than colleagues to be respected. In the 1960s and 70s, Rubin and her collaborator Kent Ford turned the Doppler technique, measuring how the light from specific spectral lines shifts in wavelength depending on whether an object is moving toward or away from the observer, to the question of galactic rotation. They began with Andromeda. It was close, it was well studied. Its stars and gas clouds could be measured in detail across the full width of the visible disk. The measurement required patience of a particular kind. Night after night, pointing the spectrograph at different positions across Andromeda's face, recording the spectra of the light arriving from stars and ionized gas at each position, measuring the wavelength shifts with precision, converting those wavelengths into velocities, mapping those velocities across the galaxy. The result should have been a Keplerian curve, fast near the center, slower toward the edges, matching the distribution of visible mass. The result was flat. Stars at the edge of Andromeda's visible disk were moving as fast as stars near the center, sometimes faster. The rotation curve refused to decline. Rubin understood what this meant. Either gravity worked differently at galactic scales than anywhere else it had been tested, which seemed unlikely given the precision with which general relativity and Newtonian gravity had been verified, or there was mass that was not visible. Mass spread throughout the galaxy and extending well beyond its visible disk. Mass that affected the rotation of the stars but emitted no light. She and Ford extended their measurements to other galaxies, dozens of them. Every galaxy they measured had a flat rotation curve. The effect was universal, not a fluke of Andromeda's particular history, not an artifact of measurement, a property of galaxies as a class. Rubin published. The field was skeptical. Some dismissed the results. Some proposed exotic modifications to gravity. Rubin continued measuring. The data was unambiguous. Eventually, the consensus shifted. Dark matter became the standard explanation for galactic rotation curves. It was incorporated into the standard model of cosmology. It became the foundation of our understanding of how galaxies form and how the large-scale structure of the universe evolved. Vera Rubin never won the Nobel Prize. She was nominated repeatedly. She died in 2016 at 88 without the prize. The Nobel Prize in Physics cannot be awarded posthumously. The work that revealed that 95% of the universe is made of stuff we cannot see, work that began on a cold night at the spectrograph looking at Andromeda's rotation curve, remains unrecognized by the award that the scientific community uses to mark its highest achievements. The dark matter that permeates Andromeda, that extends its halo to overlap with ours, that will shape the dynamics of the merger, we know it is there because Rubin looked and measured and published and was ignored and kept looking. The smear of light in the autumn sky carries her name as much as Hubble's. Let's talk about what happens at the exact moment of closest approach, the gravitational crescendo that will define the merger's most dramatic phase. Closest approach, periapsis, will occur when the cores of the two galaxies, having fallen toward each other across the shrinking distance, pass through their point of minimum separation. Current simulations suggest this may happen at a separation of as little as a few tens of thousands of light years. The Milky Way's disk is 100,000 light years across. Andromeda's is 220,000. At closest approach, the cores of the two galaxies will be separated by less than the width of either disk. At this moment, the tidal forces will be at their maximum. Stars in the outer regions of each galaxy will experience gravitational pulls from the opposite direction to what they have known for billions of years. The outer disk stars, loosely bound, far from the center, held in their orbits by the combined gravity of the galactic core and the dark matter halo, will be most susceptible to being flung outward in tidal streams. The simulations produce images that look like violence. Long, curving arms of stars thrown outward from each galaxy, arcing into intergalactic space. The two cores, surrounded by the remnants of their original disk structures, interpenetrating and mixing. The overall shape of the system at closest approach, if you could photograph it from a distance of, say, 50 million light-years, would look nothing like either progenitor. It would look like a system in the act of destroying itself and creating something new. In the center of this violence, the two supermassive black holes. At closest approach, they will be within tens of thousands of light-years of each other, far enough that they do not interact directly, but close enough that their gravitational influence on each other's environment is significant. Gas flows, stars are perturbed. The stage is set for what will eventually be the final in-spiral. After closest approach, the galaxies separate, dragged apart by their relative velocity, slowed but not stopped by gravity. They recede from each other, still bound, still falling, beginning the long arc that will bring them back for a second pass. The second pass will be slower. More energy has been lost to tidal disruption and gravitational radiation. The separation will be smaller. The subsequent passes will be smaller still. Each pass is a chapter. The merger is not a single moment, but a sequence of encounters, each one bringing the two systems closer to coalescence, each one transforming the combined structure further from its origins. We will not see any of it, not because of distance, because of time. The merger begins in 4 billion years. Humanity, as it currently exists, has perhaps tens or hundreds of millions of years left on Earth before the sun's increasing luminosity makes the surface uninhabitable, regardless of anything we do. The merger is scheduled for billions of years after we are gone. We observe the prequel. The collision itself is a story told to no one who exists now. Let's talk about what we can learn from Andromeda that is relevant not in 4 billion years, but now, about the processes that govern galaxy formation and how those processes shaped the world we live in. Andromeda is currently forming stars at a rate of roughly half a solar mass per year. The Milky Way forms stars at roughly 1 to 3 solar masses per year. Both rates are relatively modest compared to the peak of cosmic star formation, which occurred roughly 10 billion years ago, when the universe was a few billion years old, and star formation rates in large galaxies were 10 to 100 times higher. The declining star formation rate in both galaxies reflects a broader trend in the universe: the gradual consumption of cold gas, the fuel for star formation, as it is either converted into stars or expelled by stellar winds and supernovae. The universe was once a much more vigorous place, full of rapidly forming stars, young, hot galaxies glowing blue with new stellar births. What we see now, in Andromeda, in the Milky Way, in the galaxies around us, is the quieter middle age of the universe. The peak of activity is 10 billion years in the past. The current epoch is characterized by slower processes, older stellar populations, lower star formation rates. We live in the afternoon of the universe's active era. This has a specific implication for the question of life. The chemical enrichment of galaxies, the build-up of heavy elements through successive generations of stars, takes time. The first stars contained no heavy elements at all. Subsequent generations contained whatever heavy elements previous stars had produced and dispersed. Carbon, oxygen, nitrogen, phosphorus, the elements that make biochemistry possible, become more abundant with each stellar generation. We live in a universe that has been running its stellar chemistry for 13.8 billion years. The carbon in our bodies was made in stars that lived and died before the sun formed. The oxygen we breathe was forged in stellar interiors. The phosphorus in our DNA was synthesized in supernova explosions. An earlier universe, chemically poor, running its first generations of stellar nucleosynthesis, would have been less hospitable to life as we know it. Life of our kind, built from carbon and oxygen and phosphorus, requires a universe that has been running long enough to produce those elements in quantity. We are timed to this universe. The fact that we exist now, rather than earlier, is not a coincidence. The chemical conditions for our kind of life required the universe to be approximately as old as it is. Andromeda reflects the same timing. Its stellar populations include old stars from its early history, and younger stars formed from material enriched by those old stars' deaths. It is a record of chemical evolution, of the build-up of complexity over cosmic time, of the universe gradually creating the conditions for things like us. The smear of light in the autumn sky is not just a galaxy. It is a record of the chemistry that made you possible. Let's talk about the most astonishing angular scale problem in astronomy, the relationship between Andromeda's actual size and its apparent size, and what that relationship reveals about the nature of cosmic distance. Andromeda's disk spans about 220,000 light-years. At a distance of 2.5 million light-years, simple trigonometry gives its angular diameter as roughly 5 degrees, 10 times the apparent width of the full moon. 5 degrees. That is a large object in the sky. Held at arm's length, it would span a hand width. In a photograph with a wide enough field of view, it would be an unmissable structure. But the part of Andromeda that photographs easily, the bright central bulge and the inner disk, appears much smaller. Most photographs of Andromeda show a bright central region surrounded by a moderately extended disk, spanning perhaps half a degree to a degree. The galaxy looks modest in size. The discrepancy is real, and it reveals something important about the nature of what telescopes and cameras see. The outer disk of Andromeda, the extended, low surface brightness regions that contribute most to its true angular size, is genuinely faint. The material is there, the stars are there, but they are spread over such a large area of sky that the light per unit area, the surface brightness, is very low. Below the threshold of what photographic film and many electronic detectors can easily record. Below the threshold of what the dark-adapted eye can detect against the background glow of the sky. To see the full extent of Andromeda requires careful imaging, long exposures calibrated to reveal faint surface brightness structures, with sky background subtracted precisely. When this is done, the galaxy expands dramatically. The tidal streams and extended halo structures visible in deep imaging span far more than the bright core. Andromeda's full extent, captured in dedicated deep images, covers an area of sky roughly 20 times larger than the conventional image suggests. The galaxy is there. It spans 5 degrees of sky. We simply cannot see most of it because most of it is faint, and most of what we see, the bright central region, represents a small fraction of the whole. This is a broader lesson. The universe we can easily see is a bright fraction of the universe that exists. The faint, extended, low surface brightness structures, tidal streams, stellar halos, the outer reaches of dark matter distributions, contain real material and real history. They are harder to see. They require more care, more sensitivity, more calibration. But they are there. The easy universe is not the whole universe. The part that lights up readily in a short exposure is not the part that carries the most information about history and process. The most revealing structures are often the faintest. This is true of Andromeda specifically. It is true of galaxies generally. And it is possibly true of the cosmos at large. The structures we see readily may be the tip of something far more extended, far more complex, far harder to detect than what a casual observation reveals. Let's talk about the role that Andromeda plays in cosmology right now, as an anchor for measurements that extend across the observable universe. The distance ladder, the chain of measurements by which astronomers determine distances at increasing ranges, has Andromeda as one of its most important rungs. The calibration of Cepheid variables in Andromeda, Hubble's original use of Leavitt's period luminosity relation, established the first extragalactic distance scale. That calibration has been refined over decades, and Andromeda remains one of the key benchmarks against which other distance indicators are tested. More recently, the disagreement over the Hubble constant, the rate at which the universe is expanding, which determines the relationship between distance and recession speed at cosmic scales, has become one of the most discussed problems in cosmology. Two broad classes of measurement give different values for this constant. The local universe measurements, using Cepheids calibrated partly through Andromeda, combined with Type 1a supernovae, give a Hubble constant of approximately 73 km per second per megaparsec. The early universe measurements, using the cosmic microwave background, give approximately 67. The discrepancy, at roughly 10%, is statistically significant and has not been resolved. This disagreement matters because the Hubble constant is fundamental. It determines the age of the universe, the distances to remote galaxies, the size of the observable universe. A 10% discrepancy in the Hubble constant propagates to a 10% uncertainty in all of these derived quantities. And Andromeda sits at the base of the chain. If the Cepheid calibrations that anchor the local universe measurements are systematically off, if there is a bias in how Cepheid distances are measured in Andromeda and nearby galaxies, that bias would propagate to every measurement built on top of it. Several missions have been directed at this question. The Hubble Space Telescope conducted an extensive campaign measuring Cepheid distances in nearby galaxies. The James Webb Space Telescope has begun its own measurements, with the aim of cross-checking the Hubble Space Telescope results at higher sensitivity and with different systematic error profiles. Early Webb results suggest the Cepheid calibrations are robust. The discrepancy is real, not an artifact of measurement bias. Which means something about our understanding of the universe is wrong. Either the early universe measurements are biased in an unknown way, or the local universe measurements are biased, or, and this is the option that excites cosmologists the most, there is new physics that has not been accounted for. Some ingredient in the universe's history or composition that the standard cosmological model is missing. Andromeda, at the base of the distance ladder, is implicated in one of the most significant unresolved problems in modern cosmology. The galaxy that Hubble used to prove the existence of other galaxies is now a reference point in the hunt for physics beyond the standard model. 100 years from Hubble's original paper, Andromeda is still doing the same work, still being measured, still yielding surprises, still telling us that what we thought we knew is incomplete. Let's talk about the emotional logic of what Andromeda means, the specific way that understanding it changes what the sky feels like when you stand under it. Before you knew what Andromeda was, the night sky was a collection of individual objects: stars, planets, the moon, the Milky Way band. Perhaps the smear of Andromeda, noticed but not understood. The sky was present tense, things that exist now, around you, in your world. After you understand Andromeda, the sky becomes past tense, layered, historical. The light reaching your eyes from different objects left those objects at different times. The moon you see is 1.3 seconds ago. The Sun is 8 minutes ago. The nearest stars are years or decades ago. The Milky Way's galactic center is 26,000 years ago. Andromeda is 2.5 million years ago. You are not looking at the sky. You are looking at a cross-section of history with different depths visible in different directions. Every object at a different distance is a different moment in the past, preserved in the light that has been traveling since that moment toward you. The universe, understood this way, is not a collection of things. It is a collection of events observed with varying delay. The Andromeda you see is not the galaxy that is approaching us. It is a record of the galaxy that was approaching us 2.5 million years ago, when the light now reaching your retina began its journey. The actual Andromeda, as it exists at this actual moment, is invisible to you, inaccessible. The information about it is in transit, en route, not yet arrived. It will arrive in 2.5 million years. You can never see Andromeda as it is, only as it was. This is true of everything beyond Earth. The present tense of the universe is inaccessible to observation. All observation is history. All telescopes are time machines. All astronomy is archaeology. And the archaeology gets deeper the further you look. The James Webb Space Telescope, looking at galaxies 13 billion light-years away, is doing archaeology that reaches back to within 1 billion years of the universe's beginning. It is not observing the current universe. It is observing a universe that no longer exists in that form. A universe of young, hot, irregular galaxies that have long since evolved, merged, aged into the structures we see around us today. The sky is a record of everything that ever produced light. Every photon in every telescope ever built is a message from the past, carrying information about a state of the universe that no longer obtains. The universe we know is the universe that was. The universe that is remains, in the present tense, beyond reach. Andromeda, which appears to be a simple smear of light, a thing you can see with your naked eyes if the night is dark enough, turns out to be a window into this radical epistemic situation. It looks close. It looks present. It looks like something happening now. It is 2.5 million years old. The universe you see is not the universe that is. It is the universe that was, received with delay, carrying the past into your present. You are surrounded at every moment by the echoes of things that have already changed, already evolved, already become something else. The sky is full of ghosts. Ghosts of galaxies as they were before our species walked the Earth. Ghosts of stars that have since died. Ghosts of light that left its source in a universe where none of the things we call familiar yet existed. And in 4 billion years, Andromeda will stop being a ghost in our sky. It will arrive. The delay will end. The light we have been receiving from 2.5 million years ago will be replaced by light from something immediately present. A galaxy that has merged with ours, whose stars are now our stars, whose history is now our history. The arrival of Andromeda will be the end of the most ancient delay in our local universe, and by then there will be no one left who remembers waiting. Let's talk about what all of this, the scale, the approach, the merger, the isolation, the long darkness, means for the question of significance. This is the question that scale always poses. The universe is large, we are small. The timescales are vast, we are brief. The structures are incomprehensible, we are comprehending them. What follows from this? The easy answer is diminishment. We are nothing. Our concerns are nothing. The merger of Andromeda with the Milky Way will proceed regardless of anything we do. The long darkness will come regardless of anything we build or discover or preserve. On the timescale of Milkomeda, our entire civilization, every human being who has ever lived, every art and science and institution and memory, is a rounding error too small to affect the outcome. This is true. It is also incomplete. The universe produced the capacity to understand the universe. Not everywhere, not easily. Here, in this specific place, through 4 billion years of chemistry and selection, in creatures who evolved for completely different purposes, it produced something that can look at a smear of light in the autumn sky and know from first principles that it is 2.5 million light years away, that it contains 1 trillion stars, that it is falling toward us at 110 kilometers per second, that it will arrive in 4 billion years, and that the merger will take 2 billion years to complete. This knowledge, the fact of it, the precision of it, the chain of human effort and ingenuity that produced it, is not nothing. It is not a small thing. It is not a rounding error. It is the universe doing something it does almost nowhere else, becoming aware of itself, measuring itself, understanding its own structure, its own history, its own future. Andromeda did not need us to be falling toward us. It has been falling since before we existed. It will arrive long after we are gone. The physics does not require our presence, but the knowledge of it, the fact that something in this galaxy, on this planet, has reached out with instruments built over centuries of accumulated understanding and touched the light from another galaxy and decoded from that light the distance and the velocity and the trajectory and the history. This is not required by physics either. It is additional. It is extra. It is the universe exceeding what the universe requires. The scale of Andromeda is not a statement about our insignificance. It is the stage on which our significance, small, local, brief, real, plays out. The collision will happen, the merger will occur, the isolation will come, the long darkness will follow. And in the brief window before any of that, right now, in this specific moment of cosmic time, in this specific location in the local group, on this specific rock orbiting this specific star, something knows it. Something looked, something measured, something understood. You are that something. The smear of light in the autumn sky is waiting. Let's talk about the moment, the specific, physical, unrepeatable moment when Andromeda becomes visible to your naked eye. You are outside. The sky is dark enough. Your eyes have adjusted. It takes 20 minutes for the pupils to fully dilate, for the rod cells in the retina to reach their maximum sensitivity. You know where to look. From the constellation Andromeda, following a chain of stars, arriving at a position where the sky seems slightly brighter than it should be. A smear, a diffuse brightening that disappears when you look directly at it and reappears when you shift your gaze slightly to the side, letting the more sensitive edge of your retina catch it. That moment of catching it, the moment you see it, is one of the strangest experiences available to any human being. The photons landing on your retina left Andromeda 2.5 million years ago. They have been traveling across intergalactic space since before our species existed. They have crossed 2.5 million light years of near vacuum, through the outer halo of our own galaxy, through the thin gas of the local group, down through Earth's atmosphere, through the optical medium of your eye's lens, to land on a rod cell at the back of your retina and trigger a nerve signal. They arrive at you, and your brain processes them as the smear in the sky. Between the source and the observer, between 1 trillion stars burning in another galaxy and the nerve signal firing in your visual cortex, is one of the longest journeys any piece of information ever completes. Not the longest in the observable universe, but the longest available to naked human sight. You are the endpoint of a 2.5 million year journey that those photons took through empty space. That is what looking at Andromeda actually is. Not a fact about a distant object, an event completed by your looking that has been in progress since long before anyone alive was born. The universe sent a message. You received it. Thought process. Go outside tonight, find the darkest sky you can reach. Drive away from the city if you have to. Wait for your eyes to adjust. 20 minutes. Let the pupils open fully. Let the rod cells wake up. Then find it. Follow the chain of stars in the constellation Andromeda, Alpheratz, Merak, Almach, and drift just north of the line. Look slightly away from where you expect it, letting the edge of your retina catch what the center cannot. And there, in the darkness between the stars, you will see a smear, a faint, diffuse brightening, elongated, pale, something that seems less like an object and more like a stain on the night. That is Andromeda. 1 trillion stars, 140,000 light years across, falling toward you at 110 kilometers per second, containing dark matter halos already overlapping with ours, carrying a supermassive black hole hundreds of times more massive than the one at the center of our own galaxy, destined in 4 billion years to arrive, to pass through us, and through us again, and slowly, over 2 billion years of gravitational chaos, to become the same thing we are. All of that compressed into a smear your thumb can cover. The light you are seeing left Andromeda 2.5 million years ago, before Homo sapiens existed, before Neanderthals, before any human hand had ever held a stone tool. That light has been crossing intergalactic space since a time so remote that every human civilization, every language, every name ever given to any star, all of it has fit comfortably inside the final fraction of its journey. It has been traveling toward this moment, toward your eyes specifically, on this specific night, for longer than our species has been capable of looking up. And now it arrives. This is what distance means at galactic scales, not a number, not an analogy, a delay, a gap between the universe sending and the universe receiving, between Andromeda existing and you knowing it exists, between the event and its witness. You are the witness of something that happened 2.5 million years ago. There is no other way to say it. The universe sent this light before we were here to receive it, and we were here when it arrived, and that coincidence, that accident of timing, is the only reason this moment is possible. Now consider what is coming. In 4 billion years, Andromeda will no longer be a smear in the autumn sky. It will be everything. It will fill the sky from horizon to horizon, a vast, complex, evolving structure of interacting stars and tidal streams and colliding gas clouds. It will grow brighter over millions of years. It will change shape as the merger proceeds. The night sky of Earth, if anything is alive to see it, which is unlikely, will be unrecognizable. Not one small galaxy visible to careful eyes in darkness, an entire second galaxy superimposed on everything. And then, over 2 billion years, the chaos will settle. The two spirals will become one elliptical. The star formation will slow. The night sky will darken. The merged galaxy will age. Its stars will die, one by one, over trillions of years, until the last red dwarf flickers out and the only light left is the faint glow of cooling stellar remnants. And the sky, then, will be dark in a way that the sky has never been dark for us. Not dark with the darkness of a clear night full of stars at every distance. Dark with the darkness of after. After the stars, after the light, after the brief, bright era that we inhabit, that we have always inhabited, that seems permanent because we have never known anything else. We live in the bright era, the lit universe, the cosmological morning, when stars are still forming and galaxies are still active, and light fills the sky in every direction. Andromeda, falling toward us, is a reminder that this is not the permanent state of things. It is a phase, a chapter, a window that opened at the Big Bang and will close, slowly, over the trillions of years ahead. We exist in the window. Not by accident exactly. The conditions for our kind of chemistry and biology required the universe to be approximately this old, this enriched with heavy elements, this stable in its star-forming regions. We could not have existed earlier, but we could have not existed at all. The window is open, we are inside it, and the window will close. The light from Andromeda is 2.5 million years old. The light from the last stars of Milkomeda will be trillions of years in the future. Between those two moments, between the ancient light arriving at your eyes tonight and the final light fading from the last dying star of the merged galaxy, everything we call history will have occurred. Every war and discovery and love and loss and breakthrough and failure. Every species that will ever walk or swim or think on any world around any star in either galaxy. Every thought that will ever be thought. Every question that will ever be asked. All of it fits inside the gap between the light you are seeing now and the light that will eventually stop. This is your context. This is where you are in the story. A creature on a rock, in a galaxy falling toward its neighbor, in a universe still young enough to be full of stars, looking up at a smear of ancient light and knowing, through centuries of accumulated human effort, through Leavitt's ruler and Hubble's photographs and Rubin's spectrograph and the cold nights of 1,000 astronomers, exactly what it is. The universe does not know you are looking, but you are looking, and knowing, and understanding what the smear means, and where it's going, and what it carries, and what it will become. That understanding does not change the physics. Andromeda will arrive on schedule, whether or not anyone is here to see it. The merger will proceed. The long darkness will come. But right now, in this specific moment, before all of that, the light is arriving, and something is here to receive it. Go find the smear. It has been traveling toward you for 2.5 million years. Don't make it wait any longer. Good night.